This video demonstrates non-Cartesian coordinated motion using an Omron NX controller. The mechanical apparatus is a 2D particle-planar cable robot consisting of two spools that control the length of separate cables passing through points A and B and joined at the operational point P. Each spool is connected to a Teknic ClearPath-EC servo motor that receives position commands from an Omron NX 102 controller. This setup also uses a Winetek HMI for the supervisory interface to modify and trigger the motion plan. The work involved for building this demonstration includes kinematics, a motion plan, execution control, a supervisory interface, and a homing sequence. Most of the mathematics relate to the kinematics and motion plan, but I would say that 90% of the work for this demonstration was in designing a robust execution control and supervisor interface. It's important that the right motion parameters be applied at the right time and that the execution be triggered only under the right conditions. To ensure correct timing, you need to have a solid understanding of the order and timing for which the controller processes the programmed instructions. If you're interested in learning about these topics, I encourage you to check out our workshops on PLC programming, HMI integration, and motion control. Details of these workshops can be found by following the link in the video description. In this video, I'm going to share the kinematic equations, the motion planning and execution strategy, the homing sequence, and I will also demonstrate the application. The kinematics involves defining the coordinate systems and the relationships between them. This demonstration uses an actuator coordinate system and a separate task coordinate system. The actuator coordinates are the cable lengths from point A to P and from B to P. The task coordinates are the xy positions of point P relative to the origin midway between points A and B. The forward kinematic mapping was determined using trigonometry, specifically the law of cosines. The inverse kinematic mapping was determined using the Pythagorean theorem. The motion plan involves defining a path in the task space and defining a trajectory for how the path will be traversed over time. The motion planning and execution strategy depends on the controller's features and the programming instructions available. Omron NX controllers use PLC Open motion control instructions. These are standardized motion control instructions that many different vendors support. PLC Open motion control instructions operate on an axis reference object. The content of the axis reference object is implementation dependent, meaning that it will vary between vendors. I have a separate video that covers the axis configuration for these Teknic ClearPath-EC servo motors. Virtual axes can also be created. A virtual axis is not linked to an input or output device, but they are mathematically useful for coordinated motion applications. Some years after the initial specification of the PLC Open motion control instructions, new instructions and capabilities were released for coordinated motion, and the concept of grouping axes was introduced. By defining an axis group, you can take advantage of certain coordinated motion instructions, such as MC move linear absolute and MC move circular 2D. Unfortunately, these instructions only work for Cartesian robots, so a different approach is required. Instead of relying on a built-in function for the path generation, the path in the xy task space can be defined with a user-defined function. The path should be parameterized by arc length of the path. A virtual axis and the MC move absolute instruction can be used to define the trajectory and to execute the motion along the arc. The MC stop instruction can be used to interrupt the commanded motion. The MC set position instruction can be used to re-zero the arc length each time motion completes, or when the task path is updated. The XY position commands can be converted to the actuator coordinates using a user-defined function containing the inverse kinematic equations. The MC group sync move absolute instruction can be used to send those commanded position targets to the servo drives. The sync move absolute instruction allows the target position to be updated each execution cycle of the program. This feature is critical for this strategy. It also places a burden on the programmer to ensure that the commanded positions are updated without discontinuities. And finally, before any coordinated motion is possible, the servo drives need to be homed. The homing strategy I used was to manage the torque limits and perform positional move commands while observing the following error to identify when the cable is at zero length. Instead of talking through the sequence, I'm going to demonstrate the application. The application starts with the homing sequence. I'm going to show the torque limits so you can see how they vary in different stages of the homing sequence. Once the homing is complete, the kinematic equations can be used to accurately determine the XY position of point P. And we can use that to show an image on the HMI of where the operational point is. For the jogging application, I'm assigning a target position at the boundary of the workspace in the direction of travel. The shape on the screen I show just so you can easily see that we're moving in a straight line. In the linear 2D application, we're moving to a target position, and it can make a diagonal move. For jogging in the actuator coordinates, the motion is not in a straight line in the task space. On the HMI, the target position is shown by a red dot, and it can be updated so you can see the new path plan. In the Circle 2D application, the target is expressed with the center point of the circle, and the radius is relative to the actual point. So I'm just disabling the motor and turning it here, and you can see the trajectory update. When the angle is set to 360, we make a full circle. The motion parameters can be updated to adjust the timing in which we traverse the path. The velocity, acceleration, and jerk parameters, they are expressed as limits, not necessarily attained, depending on the distance of the arc. If we re-execute during motion, it resets the total arc length that is traveled. If we switch applications to a different one, motion will stop. And that concludes the demonstration.